There is zero doubt in my mind as a clinician who works with people with treatment-resistant mental illnesses that ketogenic diets can be life-changing for some people. The very first signs of Parkinson's disease and Alzheimer's disease are almost always mental illness symptoms. Once they become moderate and severe, psychosis, hallucinations, and delusions are actually common in people with both Parkinson's disease and Alzheimer's disease. In most psychiatric disorders and most neurodegenerative disorders, we have known for years now that these disorders are associated with impairment in autophagy. Ketogenic diet changes neurotransmitters. Ketogenic diet also improves insulin signaling and glucose regulation and mitochondrial function within brain cells. Ketogenic diet results in reduced brain inflammation, so it is not a lifetime treatment. It is a 2 to 5 year treatment to heal your brain. Most people can stop it, and they appear to be recovered. They remain in remission.
Chris, I feel like a lot of people coming to the conversation today are going to be coming to it from a place of hopelessness, having tried different medications, psychotherapies, diets, lifestyle modalities, so things that are natural and within the conventional realm without a whole lot of success. So given that, let's give people the 30,000-foot view of why what you're bringing to the table today is different.
I think all of those are really important points. And the reality is that we have a mental health crisis in the United States and throughout the world. Rates of mental disorders are skyrocketing across the nation. And people are pretty desperate and hopeless. And I think, you know, the hope and the good news is that the science is finally, once and for all, coming together in a coherent way to be able to answer a fairly basic but foundational question: what exactly causes mental illness? And the reason our field has been so hopeless for so many millions of people is because up until now, we really have not been able to answer that question. We have not been able to connect the dots of the biological, psychological, and social factors and figure out how they all fit together. And what I firmly believe is that now we can begin to piece them together. It doesn't mean we have magical answers for every human being alive, but it offers sometimes entirely new paradoxical pathways to healing and recovery. And the great news is that I'm hearing from thousands of people who were actually just like those people you described. They had tried treatment after treatment, pill after pill, psychotherapy for years. They weren't getting better. They had given up all hope, and they are now thriving. And so it is a new day in the mental health field.
All right, well, let's take it from the top. Somebody, again, in that hopeless category, what do they need to do to begin?
I think step one is understand the big picture. They need to understand how biological, psychological, and social factors can come together to disrupt a person's metabolism. And that when your metabolic health becomes disrupted through those mechanisms, sometimes that metabolic dysfunction or dysregulation can take on a life of its own. So even in the case of, to just play devil's advocate, so some people will say, but it's trauma. Trauma causes mental illness. And I'm not here to say trauma doesn't contribute to mental illness, and certainly trauma causes mental illness for some people. However, I don't believe trauma universally causes all mental illnesses for all people, because I know plenty of people who have mental illness, sometimes very severe ones, who have not really had a significant trauma history. And no, they haven't repressed it. They just don't have it. And so some people are like, but you know, Dr. Palmer, Chris, it's trauma. And I'm like, yeah, I never said it wasn't. But understanding what the trauma is doing to the human body is critical in understanding how to help people heal and recover from that trauma. Because you can take the person out of that traumatic environment, you can stop the trauma, and sometimes that's enough. Sometimes that's all that's needed to help a person heal and recover. But sometimes it's not. Sometimes that person appears to be harmed, injured, vulnerable, damaged, however you want to think about it, dysregulated, that the trauma did something to the person's physiology that now has them stuck. And getting unstuck is really the key. And so understanding how metabolism puts that all together is foundational. Once people understand the big picture, then you can start to piece together the parts of a treatment plan that are going to apply to you, because everybody is unique, everybody's different. I know that probably sounds overwhelming at first because you're going to say, oh, so you're saying it's impossible to solve. Nope, I'm not saying it's impossible. They're fairly straightforward strategies, but you just need to understand the big picture and then put together the basic common sense strategies.
All right, before we get to the strategies, let's take this example of trauma and connect it to the physiology. So somebody that has that in their past, and we're going to connect that to metabolic health, which is going to be our thesis of this whole conversation. How are those two connected?
When people experience stress or trauma, either one, trauma in my mind is, some people really want to put it in its own category, and I don't think that's unwarranted. I'm fine with putting it in its own category, but they activate the same physiological pathways. So when somebody is severely stressed or traumatized, or when they are stressed chronically over long periods of time, or experience kind of maybe less intense traumas, but again, over time, they can never get up. Every time they get up, somebody knocks them down again, and they're just kind of repeatedly traumatized. When it first happens, everybody kind of knows, well, you have this stress response or the fight or flight or freeze response. Well, what is that? What is that? It is more than cortisol. It is more than adrenaline. It is actually massive changes in metabolism. And what do I mean by that? I mean, your blood glucose starts going up. Your heart rate is going up. Your blood pressure is going up. Yes, hormones are changing. Inflammation is going up. The immune system is reacting. All sorts of things are happening. And how do I think about that? So the way I think about that is that your metabolism is adapting to try to help you survive. It is giving you the fuel that you are going to need to fight or flee. And that is a metabolic process. Now, when that goes on for prolonged periods of time, we have good evidence that it can result in, some people call it allostasis and allostatic overload. It's kind of a technical term. The easiest way to think about it is your metabolism, more specifically these tiny things in our cells called mitochondria. We can dive into that if you want, but just think of it as your metabolism, mitochondria get overwhelmed, and they actually, because they're kind of running on all cylinders, trying to help you survive, they begin to become damaged or dysregulated. And why is that? Because they actually, when it's running on all cylinders, it's kind of like running your car and putting your car in neutral, but then flooring it. And the engine can actually become somewhat damaged or dysregulated as a result of that. If it's extreme or if it occurs over prolonged periods of time. And once that happens, even if the trauma stops, that dysregulation or damage to mitochondria can persist. And that leaves people vulnerable to both mental health disorders, which ones? Pretty much all of them, and metabolic health disorders, which ones? Obesity, type 2 diabetes, cardiovascular disease, premature mortality. So trauma increases your risk for both mental health and metabolic health disorders. And it's because trauma induces changes to human metabolism.
All right, let's go deeper into the mitochondria piece. Talk about what they are, where they are, and then specifically what happens when they become overwhelmed and they start to break.
Mitochondria are these tiny things in our cells that most people know of as kind of the powerhouse of the cell. And what that means is that they take food and oxygen and convert it into energy. It's in the form of ATP, which is kind of the energy currency of a cell. So that's kind of the high school version of mitochondria, a high school biology class. They're powerhouses of the cell. They take food and oxygen and turn it into ATP. There is no doubt that they do that, but in fact, they do so much more. Mitochondria are actually enormously complicated. They were actually foundational to the beginning of multicellular life, eukaryotic life, which is essentially all of the life forms that we can see with our eyes, plants, animals, other things. Any living thing that you can see with your eyes is a multicellular living organism, and its existence really depended on mitochondria at one point or another. So what else do mitochondria do? Mitochondria do so much more. So they actually control the synthesis of stress hormones, cortisol, estrogen, testosterone, other kinds of hormones. They help regulate neurotransmitter production and release and regulation. They help control inflammation, turning it both on and off. They help control the expression of genes from the cell nucleus. So they are epigenetic regulators. I could go on and on with their list of functions. So they do all of these things. And when mitochondria are producing energy, when they are revved up, the process by which they make ATP involves the flow of electrons. And these electrons are actually, you can think about them kind of like, like an acidic kind of thing that's kind of, if it gets out of where it's supposed, if it leaks out, it could be a little damaging. And that is exactly what happens. When these electrons leak out of the usual process, it creates what's called reactive oxygen species. And these reactive ROS, and this is oxidative stress. And this is what all the antioxidants are all the rage for: vitamin C, vitamin E, other blueberries. Everybody says, get your antioxidants. Why do you want antioxidants? It's to mitigate this oxidative stress. And so when mitochondria are being hyperstimulated, in the example of a traumatic or stressful situation, again, if it goes on for a prolonged period of time, when it's short-lived, the system is great. The system is highly regulated. It's highly adaptive. It helps us survive. It helps us fight and flee. It helps us do everything we need to do. So I'm not at all dissing the system. The system helps us survive. But when it goes on for a prolonged period of time, the mitochondria are just churning. Electrons begin to leak. That creates oxidative stress. And that means that that oxidative stress, because they're right there, they're the first kind of victim of high levels of oxidative stress. That oxidative stress, or acid, if you think of it that way, can actually begin to damage the mitochondria themselves. It can also damage other parts of the cell. So high levels of oxidative stress can damage any part of the cell if it gets far enough. But again, because it's being produced right there, mitochondria are most vulnerable to that effect. And then if they become damaged, then the cell can become dysregulated, if you will, or the cell can become damaged, if you will, insofar as some of its parts, the mitochondria, are now damaged. And this is a term usually called mitochondrial dysfunction. And so I know that's a lot of cell biology, and I know it probably sounds like really pointless, trivial stuff and crap. But just understanding that alone will help us develop better treatments for mental illnesses, all the way from mild anxiety, ADHD, depression, to crippling schizophrenia, bipolar disorder, and other disorders.
Okay, just to make sure I have this right, mitochondria become overwhelmed. They create this ROS, which damages themselves. I just want to make the connection between the trauma and the breaking of the mitochondria. How are those specifically connected, or do we know at this point?
We do know. So again, when you have high levels of trauma, you get high levels of cortisol. And we know that cortisol alone, so like researchers just recently in the last couple of years did some studies where they put mitochondria in a petri dish. And they just saw them churning out ATP, doing their thing, going along. And they squirted a little bit of cortisol in, and they started hyper producing ATP. So it means that you're revving up the engine. The cortisol is revving up the engine. And again, we want that. This is a good thing because it gives us energy to fight and flee. And it will stimulate processes that then result in higher levels of glucose, so that, because we need that glucose to go run. We need to run from whoever is traumatizing us. And so we need that glucose. We need the higher heart rate. We need the higher blood pressure. These are all good adaptive things in the moment. But when it goes on for a prolonged period of time, that's where this reactive oxygen species comes in. Now you're hyper-stimulating these mitochondria. They're running on overtime. They're trying their best to keep up, but electrons start leaking out. They're still being told, keep going, don't slow down, don't recover, don't try to repair yourselves, don't stop. We're fighting for our life. We are fighting for our life. You've got to keep going, keep pushing. And the mitochondria are doing their thing. They're trying to save our lives. They're trying to do their share. But they start getting exhausted, so to speak, if you will. Like, I forgive the scientists will recoil at these kind of analogies and euphemisms and other things I'm using, but I'm trying to make this understandable, and that is really understandable. Think of mitochondria as an engine. You're revving the engine. You're revving it too hard. You're pushing it too hard. You're not giving it a chance to recover. You're not giving it a chance to cool down. And acid starts leaking out. And now the acid is now damaging the very engine that's trying to save your life. And that is, again, when it comes to mitochondria, we can loosely refer to it as mitochondrial dysfunction. And now the very engines that are trying to save us, trying to give us enough energy to fight for our lives, are becoming damaged and dysregulated.
Okay, we're going to eventually connect this to the brain. But just to recap what you said there, I finally have the connection. We have the trauma, cortisol, leads to the overactive mitochondria, ROS, damaging the mitochondria. So that's the trauma piece. But let's talk about some of the other pillars that lead to this damage to the mitochondria. And then again, we'll move into what that means in the brain.
Okay. The unfortunate news is that there are lots of biological, psychological, and social factors that play a role in mitochondrial function or metabolism. So, some of the basic ones are diet or nutrition, but this includes vitamin deficiencies, nutrient deficiencies, because mitochondria need a lot of the vitamins and nutrients that we've heard of are actually critical to mitochondrial function. It's actually mind-boggling how much of what we consume flows through mitochondria. The calories that we're consuming are all flowing for the most part. Most of them, I shouldn't say all, most of them are flowing through mitochondria. So that means all the different nutrients, the carbohydrates, the protein, the fats, they're flowing through mitochondria. But a lot of the vitamins, vitamin B12, folate, other things are required. They are required for mitochondrial function. Exercise directly impacts mitochondrial function. Sleep directly impacts mitochondrial function. Sleep does a lot more than that. And obviously, all of these things do more than just specific to mitochondria. But mitochondria are actually kind of the unifying link of biological, psychological, and social factors. Light exposure, circadian rhythms, drug and alcohol use, toxin exposure, whether it's microplastics, whether it's arsenic or cyanide, all of these are mitochondrial toxins. And so a wide range of things, infections. It's probably important to mention infections because that gets into like, how would long COVID cause a mental illness? A lot of people would think, well, that has nothing to do with metabolism. And what I would say is that it has everything to do with metabolism. That the infection itself is causing mitochondrial dysfunction. And that's why some people who don't get the mitochondrial dysfunction can fight off an infection and live happily ever after and never have any serious symptoms of a mental illness. But people who maybe are vulnerable, maybe because of childhood trauma or a poor diet or some other things, people who are vulnerable, they get an infection with COVID, for example, and they might get pushed over the edge. They might get pushed over the edge with mitochondrial dysfunction because their mitochondria are kind of a little vulnerable anyway. And now there's yet another assault on them, and that pushes people over the edge. And then unfortunately, even after you've fought off the virus, you may have symptoms for months or sometimes years later. And we kind of talked about stress, trauma. There are lots of other psychological, social factors that influence it. But the easiest way to think about most of the psychological and social factors is through stress pathways and trauma pathways, that they all converge in that way. But it's all of the usual things. So if you're being bullied and teased relentlessly on the playground, yes, that's stress or trauma. If you're lonely, nobody pays attention to you, that is traumatic or stressful for a lot of people. And on and on and on. So, yeah.
Okay, I can see how stress, trauma acts on the mitochondria. You brought in nutrient deficiencies and how we need certain nutrients for those to work properly. When it comes to the other factors, how many of those relate to the ROS and the damaging of the mitochondria that way?
Ultimately, that's a good question. I think most of the scientists who think about mitochondrial dysfunction think about it in terms of ROS and oxidative stress. But in fact, as I said earlier, mitochondria are extraordinarily complicated, and they do so much more than just create energy. And they do so much more than just flow electrons. They actually are going around cells and, again, they are one of the primary regulators of calcium in cells, for example, and that's a really important cell signal. They're primary regulators of inflammation. They are regulating gene expression. And all of those things are happening through a lot of complex different mechanisms and pathways. Mitochondria, fascinatingly, mitochondria can change their shape. Usually when you see them as a little oval, like a bean-shaped organelle or something. But they actually can become like long strings almost. They can fuse with each other. They can actually form complex networks, take different shapes and stuff. And although that may seem random, shockingly, the different shapes that they take at different times during cell development actually directly influence which genes get expressed, and that ultimately influences what that cell becomes. So mitochondria play a role in neurodevelopment, is what I'm saying, and development of other cells, all cells. But they are playing so we know that all those factors, those biopsychosocial factors, are influencing mitochondria. We know that they are influencing metabolism and mental health. But the precise mechanisms, like is it all ROS? We really actually don't know, and I suspect it is not at all as simple as just ROS, that it's actually probably some of these other complex mechanisms that, like, when you do this to mitochondria, it changes the gene expression in the cell. And when you do that to mitochondria, it does something different. At the end of the day, there's this like big complicated black box, so to speak. Like, okay, so you're saying biopsychosocial affects metabolism in mitochondria, and that's kind of this complicated black box in a way, if you will. We actually don't need to know the details of that complicated black box because the solutions don't require us to understand the details of that. The solutions sometimes, again, can be counterintuitive, can be paradoxical even, but the solutions can help people heal and recover. And we can help people reset their mitochondrial health or reset their metabolic health by some basic strategies. And that can help people with mental illnesses.
We're going to get there real soon, but I think it's important we talk about the connection of the mitochondria to the brain first and the physiology there. So now we know there's these different factors that come into play. They cause the ROS in the mitochondria, damage the mitochondria. They're not performing as well. How does that link to mental illness?
So at the end of the day, all of the cells in our body require the appropriate amount of energy and appropriate regulation of their function. So energy and regulation of function, whether it's a muscle cell that's contracting or whether it's a brain cell that's supposed to be firing and helping us remember something, or a different brain cell that helps us move our arm, or a different brain cell that triggers an emotion. At the end of the day, all of those cells depend on energy and mitochondria to regulate what they are supposed to be doing. And when mitochondria become dysfunctional or dysregulated, it means that the cells in our brain and body can become dysfunctional or dysregulated. And that can result in symptoms that we might call mental illness. It can also result in symptoms that we might call neurological disorders, like Parkinson's disease or Alzheimer's disease or seizures. But it but when other brain regions are impacted, maybe to a lesser extent, it can result in crippling depression or panic attacks or auditory hallucinations or delusions.
One thing that's really interesting when it comes to the brain versus the rest of the body is that the brain can't use fatty acids, or at least not to a great extent, as an energy source. So when we start to have metabolic complications and we can't use glucose as a fuel as efficiently, unlike the rest of the body, the brain can't use the fatty acids to fuel.
But it can use something derived from those fatty acids called ketones.
Exactly. Talk about that piece.
So the body actually has this really kind of elaborate and sophisticated rescue fuel system in place. And it was really probably the obvious reason for it. Like when it comes to like, why do our bodies do this? Like we're really just guessing. But you look at evolution or you look at like survival and try to figure it out and try to piece it together and try to at least make sense of it. So that's what I'm doing right now is I'm just trying to piece together like, how does this work, or why would this happen, or why would our bodies even have this feature? The most obvious reason for this feature is drought or famine. So when we go without food, we need a rescue fuel source, and that means we need to start tapping into fat stores. And if we don't have fat stores, we need to start making other fuel sources, and we can actually make glucose from our muscle. But one of the primary parts of this rescue fuel system are these ketones. And this happens primarily in our liver. So when you are fasting or starving or on a fasting mimicking diet, also known as like a ketogenic diet, and there are other kinds of fasting mimicking diets, but when you're in any of those states, your liver actually starts taking fatty acids and mobilizing them. So your whole body, your adipose cells, your fat cells are actually starting to release. Like it's this whole orchestrated event. And it really is about survival. Your whole body is, all of the cells and tissues in your body are like, okay, let's go. Let's try to save this person. We're not going to die yet. We're not going to die yet. Even if we don't have food, we know how to do this. We know how to survive. So your fat cells will say, okay, we're ready. We're going to start releasing some fat. The liver cells will take that fat, and break some of it up and release it as fatty acids, which can be used by muscle tissue and some other organs. But as you said, fatty acids have trouble getting into the brain. So what the liver is also doing is creating these molecules from those fatty acids called ketone bodies. And ketone bodies can cross the blood-brain barrier and then fuel neurons. And ketone bodies are the rescue fuel source. When our bodies can't use glucose efficiently, or when glucose levels are too low, then your body actually creates ketone bodies to try to save the day, to keep the brain running on some type of a fuel source. And those ketones end up having tremendous, it gets super complicated, but it's more that they are so much more than just a rescue fuel source. They're doing all sorts of things to help heal the body and to help the organism adapt to adversity.
Well, let's connect them to the mitochondria, which has been a big part of our conversation to this point. How do they go about using ketones?
Fascinatingly, ketones begin in mitochondria. Mitochondria are actually in the liver. So the mitochondria in your liver cells are the ones taking these fatty acids and turning them into ketones. So it's mitochondria in the liver that are producing these ketone bodies. And then the ketone bodies travel up to the brain. And what is their destination in the brain cells? It is mitochondria in the brain cells. That is the destination. So it's actually ketones, if you want to think about them this way, they are a signal from mitochondria in one type of cell to mitochondria in another cell. And what they do at the mitochondria in the other cell, so the primary thing that most people focus on is they are a fuel source. So when glucose has trouble getting into the cell, or if your mitochondria are dysfunctional and have trouble using glucose effectively, magically, somehow or another, I think for these evolutionary adaptive reasons, they can oftentimes use ketones as a fuel source, even when they had trouble using glucose as a fuel source. And so the way I think about it is that in a maladaptive state, these brain cells begin to struggle, and they may only have 80%, 70% of the ATP that they actually need to be running on all cylinders. So this cell is now becoming compromised. It's not dead. It's on its path toward death if something doesn't change. And the body senses this. When that happens, that cell starts sending out distress signals. And those distress signals actually cause inflammation and all sorts of other things to happen. That cell is distressed and it is crying out for help, so to speak. It's sending signals that are crying out for help. And again, lots of things begin to happen, but one of the things is those signals make it somehow to the liver and tell the liver mitochondria, hey, yo, we need a rescue fuel source up here right away. Like, send it now. We're struggling. And so the ketones go up, they get into that cell. The mitochondria can use those ketones to produce ATP, and now the cell starts coming back online and functioning properly again.
Let's bring insulin resistance into this. And this fits into everything we've been talking about. We're just bringing it in and addressing the elephant in the room. Basically, what we've been talking about to this point is damage to the mitochondria. But let's take it from the aspect now of increased blood glucose over time, increased insulin, somebody becoming insulin resistant on their way to diabetes. And then over time, the brain not taking in the glucose. So you have the broken mitochondria, and then you can also have insulin resistance where those cells in the brain aren't taking the glucose in because of a signaling problem with insulin in the brain.
So interestingly, that story gets even more complicated than what you just said, unfortunately. So unbeknownst to a lot of people, insulin plays a profound role in brain function. But it's actually not the same role that it plays in the rest of the body. So usually in the rest of the body, insulin attaches to an insulin receptor, and then that allows glucose to flow into the cell. And a lot of people think about it as like a lock and key. Like the insulin receptor is like the lock, insulin is like the key. You unlock it, and then the door opens up and allows some glucose to go in. And that's kind of what happens in muscle cells and other cells, liver cells, and lots of other cells. In the brain, it's actually somewhat different. The most brain cells don't actually require insulin to allow glucose to get in. However, insulin is still critical to their function, and it appears to be mostly critical to mitochondrial function. So the way to think about insulin in the brain is probably it's like a neurotransmitter or a metabolic kind of hormone in the brain. But nonetheless, the bottom line is insulin resistance in the brain still results in mitochondria not being able to use glucose effectively as a fuel source. That's the bottom line. That when you have insulin resistance in the brain, or when you have impaired insulin signaling, that's what some of the scientists will say it is, that whatever you want to call it, when that happens, brain cells have less ATP. That's the bottom line. Brain cells will have less ATP because they are unable to effectively use glucose. And so ketones in that situation can also come to save the day. So if your brain cells are struggling, they don't have enough ATP, they're not using glucose effectively for some reason, maybe because of the insulin problem, ketones can still begin to rescue some of those cells and help them function more normally.
Okay, just so I'm clear. So the lock and key, the way I explained it, is how insulin and glucose work in the rest of the body.
Yes.
In the brain differently, though.
Yes.
But insulin's still important for metabolism in the cell and to the mitochondria.
100%. Everything you just said was spot on.
Okay. Because the way I understood it from a previous guest, Dr. Mary Newport, who was just recently on, that the blood-brain barrier and the cell in the brain required that lock and key mechanism to get glucose in. There was those two different barriers that could prevent it from metabolizing that fuel.
The blood-brain barrier, that is somewhat true. That the blood-brain barrier does only allow a certain amount of glucose in. But once you get to neurons, for the most part, my understanding, and I could be wrong, I'm open to being corrected, but my understanding is that neurons, for the most part, even neurons that are very sensitive to insulin and dependent on insulin action, most neurons do not require insulin to actually allow glucose to get in, for the glucose transporters to allow glucose into the cell. And the way that I think about that is that neurons are special. There is no doubt. Neurons are very special. They are more special than any other cell, I'm going to say. Maybe there are some exceptions, but they are more special than almost all other cells in the human body. And why is that? It's because neurons in the brain, for example, are permanent. You get one set of, you get one type of neuron, and that neuron is supposed to last you your whole life. Your whole life. And once they die, for the most part, there are a few that might be able to be replaced through neuroplasticity and some stuff. But for the most part, once neurons die, they die. They're dead. They're gone. And that's why stroke victims have permanent deficits. That's why, disorders like Parkinson's disease are so difficult to treat right now. Disorders like Alzheimer's disease, severe Alzheimer's disease, we often cannot reverse it. And why not? Because the neurons are dead. And it's not easy to get new neurons. Most of the other cells in the body, liver cells, heart cells, other muscle cells, kidney cells, cells in your gonads, skin cells, they can all be replaced. They die all the time. They're constantly dying and turning over, and new ones are taking their place. And that's the pattern. So the reason, again, I'm just kind of going to this evolutionary speculation about, so why would brain cells be different? Brain cells are different because they cannot be bothered by the lack of glucose. They basically have said, like, we are not going to become dead due to glucose not being able to get into the cell. So at the end of the day, it's really about glucose not being fully utilized by the cell. And almost always that ends up being due to mitochondrial dysfunction. When the mitochondria are dysfunctional, they are the ones that are supposed to be using the glucose, and then they can't use the glucose effectively.
A minute ago, you brought up something important I want to highlight. The connection here between mental health and conditions like Alzheimer's and Parkinson's, dementia, where the difference really, we're talking about metabolic health with both of these in the brain, is that with mental health issues, there's a decrease of energy in the brain. And then with these other conditions like Alzheimer's, and you brought stroke in as well, there's actually a decrease of energy that leads to death of cells and irreversible changes in the brain versus the mental health. And what we're all going to be getting to here, the fact that we can take these lifestyle changes, provide that energy to the cells in the brain. They're still there. They wake up, and there's a lot of hope with treating these conditions.
100%. Everything you just said is true. And if I could go further just to connect some of these dots, because if anybody's a little lost or if anybody's feeling skeptical, like you can't say that mental illness is related to Alzheimer's and Parkinson's, like you don't know what you're talking about. For those who don't know, the very, very first signs of Parkinson's disease and Alzheimer's disease are almost always mental illness symptoms. So yes, for Alzheimer's disease, memory impairment is almost always going to be involved because we're usually not going to even consider calling it Alzheimer's disease unless there is some degree of memory impairment. So that becomes kind of circular logic that if there's no memory impairment, we're not going to call it Alzheimer's. But for the majority of people with Alzheimer's, some of the other first symptoms of Alzheimer's disease, in addition to that mild memory impairment, are depression, anxiety, panic attacks, obsessions, compulsions, insomnia. And once those illnesses get going, once they become moderate and severe, psychosis, hallucinations, and delusions are actually quite common in people with both Parkinson's disease and Alzheimer's disease. So it's actually this kind of thinking about it through a metabolic lens actually helps us understand all of that. It helps us connect so many dots that we have not been able to connect. So it's not a serotonin problem per se. It's not a dopamine problem per se. It's a metabolic problem that, yes, can result in dysregulation of serotonin or dopamine. But we usually don't think of Alzheimer's disease as a serotonin problem. And we usually don't think of Alzheimer's disease as a dopamine problem. It is a metabolic problem. It is a neurodegenerative problem. And that's the way we need to start thinking about mental illnesses, all the way from anxiety disorders to psychotic disorders.
I like where this is going. We've started out talking about mental health. Now we've brought it into this dementia realm. And we could even further take this into things like cardiovascular health, cancer, diabetes. The good news in all this is that when we start to pull the levers, fix our metabolic health, it's going to impact the brain and the rest of the body. And arguably, when you get to the root of this metabolic health thing, it impacts all chronic disease,
Yes.
Which is just so exciting because knowing that, it's not like we need to come up with different tools and tactics for all these different diseases and problems in the body. It's like, no, there's one encompassing lever that we can pull and have such a great impact.
We could say it's one lever in terms of metabolic health or mitochondrial health, and that is absolutely true. But then you could go a step before that and talk about all of these biopsychosocial levers, which there are lots of biological factors and psychological and social things. And at the end of the day, many of them distill to this kind of field that we call lifestyle medicine. So diet, nutrition, sleep, exercise, managing substance use or reducing it, stress reduction, and relationships or purpose in life. Like those are the 6 pillars of lifestyle medicine. And by no means do I want, so for a lot of people who have mild metabolic problems, maybe they're overweight, or maybe they have prediabetes, or maybe they have high blood pressure, or maybe they have mild anxiety or depression or ADHD. Those lifestyle basic interventions can actually change people's lives, just those alone. By no means do I want anyone to come away from this conversation saying that Chris Palmer said that if everybody just followed a healthy diet and exercised, they would get rid of schizophrenia. That's not what I'm saying. Schizophrenia is a severe, life-threatening, devastating disorder. And metabolic treatment strategies can absolutely play a role. And I'm hearing from hundreds of people who are reversing their schizophrenia. That's kind of a new term. Like, we're not supposed to be talking about reversing schizophrenia, but where people are reversing it. That means they are going into remission, sometimes off antipsychotics. So is that possible? Yes, it is. But it's not always as simple as follow a healthy diet and do a little exercise and everything will be fine. It can get more complicated than that.
Exactly. I'm on the same page. What I meant by one lever is this metabolic health piece, the mitochondria. And then we have the diet and lifestyle that are different mini levers under that umbrella.
Absolutely. Absolutely.
All right. Well, one question we need to answer now that we've brought in all these different aspects into it, how come for different people, different things break, whether it be the brain, cardiovascular system, cancer, since we have one root cause being metabolic dysfunction and problems with the mitochondria?
That's one of the $1 million questions. And to be honest with you, I think for some of the skeptics, that is really the question for them. And the way that I think about it, so let me just, before I answer that, let me just take a step back, since I'm talking about skeptics and people who maybe don't get it or people who don't believe it. Let me just step back and say we actually have decades and decades of scientific evidence to support everything that we're talking about right now. So do we have evidence that ATP levels are reduced in people with high blood pressure? Do their blood vessels actually have higher levels of oxidative stress? Yes. Do their blood vessels actually, the cells that line their blood vessels, do they have lower levels of ATP? Yes. In somebody who has fatty liver disease, do their liver cells actually have oxidative stress, lower levels of ATP? Yes. Do people with obesity have lower levels of ATP? Yes. That is a shocking paradox to a lot of people. Obese people who have all of these extra calories on their body, have lower levels of ATP in their cells. Do people with schizophrenia, do their brain cells have oxidative stress, lower levels of ATP? Yes. Do people with bipolar disorder have these? Yes. With bipolar disorder, it gets a little more complicated because it depends on what phase of bipolar disorder they have. So it's about dysregulation of this ATP levels. And what I mean by that is that when they get manic, when they have too much energy, we actually see exactly that in the cells, that their cells are actually hyperactive. And they actually do have probably too much ATP. They are on overdrive. They're not slowing down. They're not following normal circadian rhythms to slow down. And so you get you can get dysregulation in either overactivity or underactivity. But to answer your question, so how do I think about why would one person have high blood pressure and another person have schizophrenia and another person have obesity? If I'm saying that they're all metabolic. Well, number one, it really depends on which cells in the body and which organs are affected. Because not all of the cells in your body are affected equally. And why is that? What helps regulate different cells? Well, lots of different factors, hormones, neurotransmitters, other things, other signaling pathways. All of those hormones, neurotransmitters, signaling pathways are actually designed to stimulate or inhibit some types of cells and not others. And that means that metabolism is this kind of complex patchwork um, of 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 cells firing and other cells slowing down. So to help you understand, to put a little context to that, if that's confusing, is that, we have this sympathetic nervous system, which is the fight or flight thing, and we have the parasympathetic nervous system, which is the rest and digest system. Some people call it that. They actually kind of do the opposite things. And that's a great example of some cells and tissues being activated or stimulated metabolically, and other cells and tissues being inhibited. So the parasympathetic nervous system will slow your heart rate down. The sympathetic nervous system will speed your heart rate up. And what that means is if you were actually measuring ATP levels in the heart cell, it'll be commensurate. And when your heart rate's going up and your heart is pumping more forcefully, ATP levels are going up. And actually, it's the ATP levels going up that's allowing your heart to do all of that. And when the parasympathetic system is trying to slow your heart rate and relax it, it's actually relaxing the metabolic rate at the same time. And so, yeah, let me shut up and ask, do you think I addressed the question? happy to
No, it's great.
Elaborate if you need. Good. Okay, good.
Let's come back to the mitochondria specifically. And we know that they're damaged by the ROS that they're producing. When it comes to regaining our metabolic health, what is the goal there? Once they're damaged, can we repair those? Are we just making new ones? Let's talk about that physiology and what our end goal is in that realm.
The body actually has this very sophisticated, elegant system to get rid of old or damaged cell parts and cells and replace them with new ones. And one term that a lot of people will use to describe that process is called autophagy. So it's the process by which your cells actually know how to identify which proteins or organelles or other parts of this cell are damaged or old, and we need to get rid of them. And when they get rid of them, what does that mean? It means they shuttle them to lysosomes where the lysosomes degrade these things, and then they reuse all the parts. Like the body is very frugal because you never know when you might have a drought or famine. So it doesn't just like dispose of them and you pee them out or poop them out. It actually recycles them. It breaks it down into their component parts of carbohydrates or fatty molecules or amino acids, and then it reuses them. And so mitochondria undergo a similar process. So there's this subset of autophagy called mitophagy, in which old and defective mitochondria or mitochondria that are dysfunctional can be shuttled to lysosomes and degraded and recycled. There are some other mechanisms through which mitochondria can actually be removed from neurons in particular and other cells. So immune cells, for example, can actually connect themselves to neurons, for example. Like there are these things called microglia, and they can connect themselves to neurons, and they actually can take on some of these old damaged mitochondria and kind of serve as the waste disposal factory themselves, so that the neuron doesn't have to be bothered with like disposing of old and defective mitochondria. There are other cells that can actually do some of this work for the neuron. But at the end of the day, it's all about mitophagy, and then you need new mitochondria to take their place. And that is a process called mitochondrial biogenesis. So essentially, when your cells begin developing mitochondrial dysfunction, the path to healing is to stimulate processes that will identify those dysfunctional mitochondria, because you don't want to get rid of the healthy mitochondria. So you want to leave them alone. But again, the body amazingly knows how to do this on its own. It can identify the dysfunctional mitochondria, get rid of them, dispose of them, and now the cell no longer has as many dysfunctional mitochondria. And so the cell can make new mitochondria to take their place. And now the cell has done what we might call a refresh. Got a cleanse, if you will. Let's cleanse the old mitochondria, the dysfunctional mitochondria, and let's replace them with new ones.
And how do we support the body in doing that?
Autophagy is something that should be happening routinely because cell parts are always becoming damaged or old. So we certainly need a low level of autophagy at all times. And in fact, in most psychiatric disorders and most neurodegenerative disorders, just sticking with the brain, we have known for years now that these disorders are associated with impairment in autophagy. So one of the primary ways to support this process is through fasting and fasting mimicking diets. And I actually think this is actually probably one of the reasons why fasting has been used for millennia in just about every culture on earth as a healing practice. Most religions use fasting. So fasting has been around for a long time. And, for a long time, I think most modern people thought that it was all just crazy talk, or even dangerous kind of stuff. Like, they're starving people. Some people equate those two terms. They're not at all equatable. Going without food is normal. You should not be eating all night, every minute of every night. So that going without food is called fasting. And so all of us should fast. Obviously, there's a certain timeline, and if you fast for too long, then at some point it tips over into what we call starvation, and that is no longer healthy or good, and it is dangerous, and you can die from that actually. But I actually think that's the reason fasting's been around for so long, is because it supports this cleansing process. It supports this process of let's get rid of any old and defective cells or cell parts. So this can apply after you've had an infection. And infections have been around for millennia. So people would get sick, 1,000 years ago, and they might get sick from an infection. And so you may wonder, why would fasting be helpful for that? Well, if some cells became dysfunctional due to that infection, then fasting actually might stimulate a healing process to help that person heal and recover. Now, at some point, you do have to reintroduce calories, because you don't just want to get rid of old cell parts. At some point, you need to start replacing them with new cell parts. And that means the cells need fuel. They need more fuel, and they will get that fuel. Interestingly, I'm saying that a lot, but interestingly, when people are fasting, so their cells are recycling all sorts of old damaged parts. It's not just mitochondria. It's misfolded proteins. It's, plaques and tangles. Those Alzheimer's things? Plaques and tangles start getting recycled. The cell starts clearing those out. Why? Because it needs fuel. It needs fuel, and it starts eating anything that it needs. Usually, when a cell is in that state, in a fasting state, it actually has processes in place to inhibit the production of new proteins and new membranes and other things, because the cell recognizes, whoa, it's famine time. We can't be producing new parts. Don't have enough fuel for that. Let's just go into survival mode. But the fascinating thing is new mitochondria are often produced in that state. So the cell actually prioritizes the production of more mitochondria. And we really don't have a clear answer of why would the cell do that. My speculation is because mitochondria are going to save the day. Mitochondria are going to send the right signals, because they're doing so much more. They're helping that cell adapt. They're changing gene expression. They're regulating calcium levels. They're regulating hormones. And so when the cell is really stressed, what does the cell do? It says, let's make more mitochondria to help save the day. We need more troops, so to speak.
Okay. In a practical sense, because there are so many different types of fasts, different lengths, are we talking about an overnight fast here? We could go all the way to a 40-day water fast. There's dry fasting. How does somebody know what type and how far to push it to get these benefits?
That's a really important question. And I'm going to say there's not a one-size-fits-all answer for that. Let me just be clear. So first and foremost, I would say there are some people who absolutely unequivocally should not fast for their health. Who would that be? People who are already starving to death and emaciated. So that would include somebody with anorexia nervosa. That might include somebody with severe like cancer who's just gone through radiation and chemo and is now emaciated, has lost a ton of weight. Those people should not be fasting. Now, we can talk about fasting mimicking diets so that they can get some of these benefits, but they need calories. They should not be going without calories. The other group that I'll put in there who should not be fasting as a rule of thumb, at least not for prolonged periods of time, would be growing children who are at least normal weight. So if a child is really obese, then maybe some fasting could be helpful if the child is interested in doing that. But normal weight growing children should not be going without calories for prolonged periods of time. And I would say pregnant women should not be going without calories for prolonged periods of time. So they are trying to produce and grow a brand new human being. And that takes a lot of calories and resources and energy and every nutrients and all sorts of stuff. And so if women start fasting during pregnancy, and we actually have good data from this, from like the famine studies of populations, that when women go without calories for prolonged periods of time while they're pregnant, that can have very severe adverse effects on their children. So those are the categories that I would say should not be fasting at all. And then to answer your question, so who should do fasting? How long? It really depends. Are we talking about somebody who weighs 600 pounds, who is severely ill, but also has a tremendous calorie surplus on their body ready to be tapped into? Well, that person, I might actually be okay with that person if they want to do a prolonged fast for 7 days, 14 days, 21 days. I would not recommend a dry fast myself. That can be dangerous, actually. So I would recommend a water fast. But if that person wants to do a water fast for a prolonged period of time, especially if they can get medical supervision to just make sure they're going to be okay through all of that, yes. And I sometimes do that with some of my patients who are really overweight and potentially diabetic and really could use some rapid improvement. And you can actually see very rapid improvement with that model. But other people, it's going to be more complicated again. So it's really about walking the line between therapeutic fasting, which has benefits and it has healing potential. And if you push the boundary too much, you end up in what's called starvation. And starvation is life-threatening and very dangerous. And so you have to know where that line is, and it's different for different people depending on those factors that I just outlined.
What about yourself? Somebody who's normal weight, understands the importance of mitochondrial health. Do you have a certain practice that you're doing weekly, daily, monthly to help keep those mitochondria healthy?
I definitely implement some type of intermittent fasting. I'm not on like a schedule, but I'll go, just a few days ago. It was more because I was so busy with work, but I just didn't eat. It really started, I had not planned to fast that day. But I was just busy and I'm like, well, I don't have time. I'm not too hungry. And then as the day went on and lunchtime came and I realized, wait, I don't know if I have time for lunch. I actually thought, oh, this will be a good day to fast. I'll just throw in a fast and call it. I'll make lemonade out of lemons of a busy work schedule that doesn't allow me time to eat. Do I do it regularly? I do kind of. I definitely skip meals, skipping breakfast, skipping lunch. Are easier for me. It's harder for me to skip dinner. When I skip dinner, I sometimes have trouble sleeping, honestly. I get a little revved up from the fast. So I personally tend not to skip dinner, but I think for people who can sleep well and skip dinner, skipping dinner is probably more therapeutic because then you go through the whole night and you get a longer window of a fast in. So I think that's more therapeutic. I think I'm just one of those people who's kind of sensitive to it. So I usually don't because I like my sleep.
So we know there's mitophagy, where different parts of old mitochondria are being recycled and reused. We know we can make new mitochondria, including using those parts. Is there any such a thing as building bigger mitochondria, increasing the density of mitochondria within a cell, doing some of this that we're talking about to create a more robust body metabolically?
Yeah, well, 100%. The clearest example, so mitochondrial density, for example, how many mitochondria are in a cell? The rule of thumb is that the more healthy mitochondria, I should say, that are in a cell, the more resilient that cell will be, the more capacity and endurance that cell will have. And do we have any evidence for that? We have an abundance of evidence for that, and it's called athletes. So athletes, really, athletes kind of sometimes, taking apart all of the talent and balance and different types of body strength that you might need and everything else. So all of that matters, and size matters because, super tall people usually are not gymnasts because they just can't contort their body in those ways or whatever. So yes, but there are two kind of buckets for athletes, and one is larger muscles that allow for more power, and the other is muscles that allow for endurance. And the muscles that allow for endurance are usually not that much bigger. Sometimes they're smaller even. And the clear example of this are marathon runners. So marathon runners, when you look at a marathon runner, if you meet them, they actually don't usually look like a big, tough athlete. They can just look like an everyday Joe. Even if they can run 100 miles without stopping. They don't look that much different. And why is that? It's because their muscles aren't much bigger. So what makes their muscle different than my muscles? Because I can't run that far. I can't run that far without stopping. So what makes their muscles different than my muscle? One and only one thing: the number of mitochondria in their muscle cells. So if you took a biopsy of their muscle cells would have abundant mitochondria, just all packed together. And if you took a biopsy of my muscle cell, it would have fewer mitochondria. They would be more spaced out. So I think that, does the same thing occur in the brain? I'm not aware of whether we have clear, compelling evidence for that, but I suspect it does occur. With liver cells, for example, we know that when liver cells have more mitochondria, they are healthier, function better. That liver is healthier, less likely to have fat, a fatty liver. The other clear example, uncontrovertible, are fat cells. So we have 3 different types of fat cells, probably more, but I'll put them into 3 buckets: white fat, brown fat, and beige fat. And as most people know, brown fat is kind of good for you, white fat is bad for you, and beige fat is kind of in between. And what makes fat cells white, brown, or beige? It's the number of mitochondria in the fat cell. Brown fat has a lot more mitochondria. White fat has fewer mitochondria, and oftentimes those mitochondria are somewhat dysfunctional. In obese people in particular, they have even fewer mitochondria, and the mitochondria are in fact dysfunctional. And what we think is happening is that their mitochondria become so dysfunctional or impaired that they can't release the fat from the cell. That is why they are stuck with fat on their body, is that their fat cells are impaired. They can't function properly. Because one of the functions of fat cells is to store fat. But an equally critically important function of a fat cell is to release that fat. And mitochondria are instrumental in that process. Mitochondria are doing a lot of the work to release that fat from that cell. So if mitochondria are dysfunctional, the fat becomes trapped, and then people just develop obesity, and it just grows and grows and shows no stopping it.
At this point, let's get really practical. Take everything we've been talking about and give people the playbook. And for an example here, we'll use mild anxiety or depression, somebody that's not suicidal, but they've been tuned in to this point. They're intrigued. They want to give this a go. What does that look like, diet and lifestyle wise? And then how long should it take before they notice a difference?
So again, there really is not a one-size-fits-all solution. And why do I say that? Because everybody's different, and that means everybody has different biopsychosocial factors contributing to their anxiety. So anxiety by no means is caused by one and only one thing, although anxiety disorders, so and again, even in this case, anxiety can be normal. So if you're being bullied and teased every day, you're going to be anxious. That's not a disorder. Changing your metabolism should not change that. The process of being bullied and teased every day is going to make you anxious. It should make you anxious. And the solution is to somehow get the bullies to stop bullying you. But if you have an anxiety disorder where you're anxious for no good reason, or you're hyper anxious, you're just more sensitive than everybody else to anxiety, then I would say you probably do have a dysregulation of your anxiety pathways in your brain. And that does relate to metabolism. and you could get better. So what could be causing that? Again, lots of things. You could have low iron could cause that. And that's really particularly relevant for women who are menstruating, because at least probably 10% of women in the United States have iron deficiency because of that. So for them, it might be check your iron levels and get some iron. For other people, it might be low thyroid hormone. So there are lots of reasons, but I'm gonna be a good sport and give you a one size fits all kind of package, or a starter package for you have anxiety, you don't know why, you're a typical American. Let me start with that. You're a typical American. So what do I want you to do? Step one, I want you to clean up your diet. You're probably eating a lot of ultra-processed foods. 60 to 70% of the foods consumed in the United States are ultra-processed foods. They are not good for you. They're not good for your brain. They're not good for your anxiety. So clean that up. Try to eat real whole foods. Second thing, if you're a typical American adult, about 33% of American adults are not getting adequate sleep. If you're a teenager, if you're a college student, you're probably in that category as well, maybe even higher rates. If you're a college student, you're probably not getting adequate sleep. So what do I want you to do? I want you to get adequate sleep. What is that? Let's go for 8 hours. 8 hours of uninterrupted sleep every night, ideally around the same time every night. So ideally going to bed around the same time, waking up around the same time. I'm a huge fan of light in the morning. So I would get some light in the morning, go out for a walk, open up the window. If you live in a place like Boston and it's the middle of winter, like I do, then maybe get a bright light at your desk or something, but get some light in the morning. If you're not exercising, add some exercise to your regimen. If you're already exercising, I actually find that adding more exercise usually doesn't help. If you're already doing the exercise, you're doing it. Don't worry about changing that up more. And I don't want people exercising excessively, because that's really stressful on the body and it's just really stressful to you. So you don't want to do that. But if you're a couch potato and you really don't exercise at all, try to move your body. It could be as simple as just get outside, that morning light that you're trying to get. Go outside and take a walk around the block. Maybe even pick up the pace and do a little brisk walk. Or if you think you're up for it, maybe a little jog. Even if you have to stop every now and then and catch your breath, do a little jog, walk, do a little jog, walk. If you're using a lot of substances, alcohol and marijuana in particular, I know this is going to break everyone's hearts. I know other people are going to yell at wherever you are right now as you're listening to this, watching this, you're going to yell at the screen or at the whatever. But I want you to back off on the alcohol and the marijuana. Now, the reason I know I say people might yell at me for that is because what I already can hear them. They're saying, but Dr. Palmer, alcohol and marijuana help my anxiety. They help it. And I don't doubt that for a second. They help it in the short run, and they make it worse in the long run. And we have abundant data to support that. So that is challenging. If you're hooked on marijuana because of your anxiety, now you're kind of stuck in a difficult place. And I'm going to encourage you to try to get off that marijuana in order to treat your anxiety. But here's the caveat. It means your anxiety is going to get worse before it gets better, because you're going to go through marijuana withdrawal. It's going to be hard to get off of it. Your anxiety will get worse before it gets better. But if you actually want to heal and recover, you're going to need to get off the marijuana. If you do not have friends and relationships, family, if you feel lonely a lot, if you feel empty, if you feel bored, if any of those things apply to you more than 2 or 3 times a week, if you feel lonely, empty, or bored more than 2 or 3 times a week, I want you to try to do something about that. Call a friend. Yes, I just said call. I didn't say text. I said call. Like actually bother them and dial their phone number and then talk. Actually, let open your mouth and let words come out and talk to them. Because texting usually is not a very good antidote to loneliness and emptiness. Maybe boredom, but it's not a very good antidote to loneliness and emptiness. Whereas talking to people and having a real conversation, like let them know I'm kind of lonely. I'm bored. I would love to hang out. Let's do something. Let's get together. Let's go for a walk in the morning together. Whatever. So have some relationships. You can do stress reduction, but I'm not going to say stress reduction because that's like the cliche. Most people with anxiety have been trying to reduce their stress. It's not working. So I'm giving you the other pointers. But if you have never tried mindfulness or meditation or anything like that, sure, give it a shot. But I'm going to assume you've already tried that and it doesn't work for you and you don't want cliche answers.
Coming back to marijuana and alcohol, are those directly damaging the mitochondria?
100%. We have known, so for alcohol, we've known that since the 1960s. Researchers have tried to figure out how exactly does alcohol poison the liver, because we know it poisons the liver. And the way it poisons the liver is through mitochondrial damage. Marijuana, same deal. THC in particular is a direct mitochondrial toxin. So yeah, really important to avoid them. Again, the unfortunate catch-22 with them, like I said before, is that, yeah, they do relax you, or they do have a short-term beneficial effect. Millions and millions of people would not be hooked on them if they didn't. Of course, they have a beneficial effect on you, but it's short-term, and it results in more metabolic mitochondrial damage that then just makes you going back for more and more. And that's how people end up in vicious cycles. And that's how people end up getting hooked on them, how people can become alcoholic, is that they need more and more and more to calm the effects. And it's tragic. It's tragic because the person's just trying to feel better and they're digging their hole even deeper and deeper and deeper every time they try to feel better.
Earlier, we talked about fasting. I'm assuming that would be a good one to add to the list you just shared for the right person.
Yes, I think fasting. So if I would actually start with the things I just said, get rid of the ultra processed foods, eat real whole food. You don't have to go without food if you don't want to. Just like if you try to clean up, do some basic lifestyle medicine things. If those things don't work, then absolutely. I probably would next go to fasting and fasting mimicking diets. So some people can fast and they don't mind it. And, initially it can be painful. People get hangry, they get irritable, they might feel weak or dizzy or other things. That is often, if you are one of those people, it actually is because you lack what's called metabolic flexibility. And what that means is that your body is really struggling to go between fuel sources, to stop using glucose and start using fatty acids and ketones as a fuel source. That will change over time. So if you practice at fasting, maybe you just fast for a few hours and then add another hour in terms of intermittent fasting. Just try to get a little longer with the fast. You'll work up that kind of muscle, so to speak. You'll be able to tolerate it better. You'll get better at it. It will become easier. for a lot of people, at some point you'll start to notice a benefit. You'll go without food. And I mean, like I mentioned myself the other day when I was kind of forced to fast because I just didn't have time to fit in the meals. By the end of the day, I actually was like, I was like noticing, like, I feel great. And I'm thinking I should do this more often because I actually feel really good. I feel really good right now. And then I ate dinner and then I slept really well that night and woke up feeling unusually better than normal. So, yeah.
I noticed when you went through the diet piece for this hypothetical patient, we didn't bring in ketosis. And this ties back to earlier in the conversation, ketones being an alternative fuel for the brain. How does somebody know whether or not including the ketogenic diet would be a worthwhile piece of this puzzle?
I would start with the basic things that I outlined. If those aren't working, then I think you need to start considering more sophisticated, advanced metabolic therapies, which include ketogenic diets, but can also include things like supplements and vitamins and other things and I don't want people taking a handful of vitamins and supplements because that can actually be harmful. So you don't want to over supplement. You don't want high levels of vitamins. You want adequate levels of vitamins and other things. But there's photobiomodulation, red light therapy, other things. So there are lots of metabolic strategies, but there is zero doubt in my mind as a clinician who works with very ill people with treatment-resistant mental illnesses, schizophrenia, bipolar disorder, chronic unrelenting depression, severe anxiety that paralyzes people. There is no doubt in my mind that ketogenic diets can be life-changing for some people. I certainly don't think everybody needs to do it. Not everybody is struggling that much, and not everybody's metabolism is that dysregulated or dysfunctional, so to speak. So the way I think about the ketogenic diet is it's an intervention, just like fasting is an intervention. Now, for some people, prolonged fasts can be really beneficial, as we discussed. And for some people with serious metabolic dysfunction, prolonged ketogenic diets, and we're really talking on the order of years, a few years at least. For some people, prolonged ketogenic diets can be life-saving. There's no doubt in my mind. And the clearest example is epilepsy, but we now have over 50 published case reports and pilot trials of the ketogenic diet being used for a wide range of neuropsychiatric disorders, Alzheimer's disease, schizophrenia, bipolar disorder, depression. OCD is just getting published by our group. Wide range of disorders and over 1,900 people represented in those published research studies and countless others, literally thousands of people reaching out to me over social media, sharing their stories of how they have healed and recovered using ketogenic therapies. With that said, it's not a one-size-fits-all treatment. With that said, it's not a panacea. If you're not sleeping well and you're using lots of marijuana, let me be the first to tell you, ketogenic diet is not going to magically fix all of that. Like, you've got to sleep. You've got to stop the marijuana. Sorry. You can't do your keto and you have your marijuana cake too. You got to give up the marijuana. And I've had patients in exactly that situation who are on ketogenic therapy. It was helpful, but the marijuana was really preventing their recovery. So I know firsthand with patients that what I'm saying is true. So it's important to do the whole treatment package, not just one thing.
Let's talk more about that multiple year thing. Somebody who is going to give this a go and they're suffering severely right now. Well, for one, they should definitely work with somebody alongside what we're talking about. But when it comes to that multiple year ketogenic diet to cause what sounds like permanent changes in the brain, do we know what happens in the brain over that multiple years?
It's a really important question. I have a speculation, and I'll share that in just a sec. But I think what we know, because being able to answer that means mechanisms of action. And usually it means having to dissect brain tissue and analyze it to see what's happening to it. We are not allowed to do those studies in humans. Let me just say that and repeat that. Human trials with mechanisms of action like that, they are impossible to do. Why? Because we are not allowed to slaughter humans after doing an intervention and then dissect their brain and analyze it. So that means we have to rely on animal studies, and the animal studies that we most rely on are mouse studies, mice and rats. Now, immediately that raises questions, concerns, criticism. Well, that's a mouse study. That's not a human. Well, okay, but we can't do this study in a human, so I don't know what you want. But what we do know from mouse studies is that ketogenic therapy, and what we know from some imaging studies in humans, for example, is that ketogenic diets change neurotransmitter balance, neurotransmitter regulation function in the short run. And so in a study of people with bipolar disorder on ketogenic therapy, the researchers found that their glutamate levels were reduced. And that is associated with what's called hyperexcitability, or an overactive brain cells or brain regions. But in a nutshell, ketogenic diet changes neurotransmitters. Ketogenic diet also improves insulin signaling and glucose regulation and mitochondrial function within brain cells. We know that from lots of animal studies and other studies, and even human studies where we can do imaging to measure some of those biomarkers. Ketogenic diet results in reduced brain inflammation. So we know that from Dr. Nora Volkow, who's the director of NIDA, a world-renowned neuroscientist. She did one of those studies in people with alcohol use disorder, put half of the people on a standard American diet, half of them on a ketogenic diet, detoxed them. And when they detoxed, one of the findings was improved brain metabolism and reduced brain inflammation. So I'll stop there with just that nutshell of kind of different mechanisms. We know that all of those things are obviously useful, beneficial. And so it may be that the ketogenic diet is just doing all of those things over time. It gets complex fast because the ketogenic diet is also changing the gut microbiome and is changing body-wide inflammation, not just brain inflammation, but in terms of changing the gut microbiome, that may be one of its mechanisms of action because there's this gut-brain connection through the vagus nerve and through other pathways that what's happening in the gut is influencing brain function. So some researchers actually are really more focused on that the ketogenic diet is changing your gut biology, and then that in turn is impacting your brain biology. So it could be through that complex mechanism. At the end of the day, what I believe is happening, and we have a good amount of evidence to support this from animal studies and others, that I believe what's happening is the process that we've talked about. That your brain cells are slowly but surely getting rid of defective mitochondria and replacing them with new and healthy mitochondria. And that your brain cells are actually increasing mitochondrial density so that they are becoming more resilient and more robust. So that after a few years, a lot of people with epilepsy, we have the most evidence within epilepsy, a lot of people with an epilepsy who can become seizure-free on a ketogenic diet are often able to stop the ketogenic diet after somewhere between 2 to 5 years and remain seizure-free. So it is not a lifetime treatment. It is a 2 to 5 year treatment to kind of heal your brain, so to speak, allow your brain to repair itself. And then a lot of patients, not all, because some people do need to do it for life. Unfortunately, we don't exactly know what's going on or why they need the ketogenic diet. But most people can stop it. Most people can stop it. And they appear to be recovered. They remain in remission. And I think what I can safely say is that somehow something happened that allowed them to heal. And whether it's through inflammation, whether it's through the gut microbiome, whether it's through mitochondria, whether it's through neurotransmitters, at the end of the day, I'm kind of like, who cares? I mean, it is interesting to me as a scientist. Great questions to answer. But for the time being, who cares? All that matters is that this person is better and has a better life and is healed and recovering. That's what matters.
If it was you and you were doing, say, 2 to 5 years on a ketogenic diet, if you were in that period of coming off it and seeing how your body reacted, would you just do, say, after a couple of years, the odd test day, ramping up the carbs for a day or two and kind of just see how you feel? Basically, somebody transitioning out, how do you guide somebody?
You know, there's actually controversy in the epilepsy field on this exact question. So some people, some neurologists who use the ketogenic diet to treat epilepsy, you know, when they decide, okay, today's the day, we're going to transition off, they'll say, eat whatever the hell you want. I don't care. Just do whatever you want. And for some patients, that works out fine. For some, it doesn't. And then they have a seizure, and then it's like, oh, you need the ketogenic diet again. I tend not to do that because when you tell people eat whatever you want, they almost always go for ultra processed junk food. And they're like, oh, I've been craving brownies and ice cream and, you know, all this kind of candy bars and everything. So they just binge eat all that. I usually tend to have people gradually increase protein levels, gradually increase carbohydrate levels in the form of vegetables and fruit, and see how they tolerate it. So I'm still keeping them on a whole food diet, real whole foods. But now they may not be in ketosis anymore if they're eating a lot of fruit or if they're eating a lot more meat. They may no longer be in ketosis. And then we just assess what's happening. If their symptoms are coming back, especially if they're coming back with a vengeance, then we know, okay, get back on the keto diet. Like you're not ready. What I find is that the longer people are on it, this 2 to 5 year thing really is true. I know that that's even a broad range. 3 years is a long time. Whether you have to do it for 2 years or 5 years, it is a big difference in the grand scheme of life. In the grand scheme of suffering from schizophrenia, it's trivial. In the grand scheme of suffering from treatment-resistant epilepsy, it's trivial. 2 years, 5 years. The real question is not 2 years or 5 years. The real question is seizure freedom or not. The real question is with schizophrenia is, do I want remission of my schizophrenia or not? Do I want to live the rest of my life disabled from schizophrenia, or do I want to recover from schizophrenia? And then the question of 2 years, 5 years, it becomes irrelevant to most people. It's like, yeah, that we'll figure it out and we'll deal with it. And yeah, it might be unfair. Yeah, it might suck, but whatever. We'll suck it up and just do it.
And do you find during that 2 to 5 years, people need to be 100% strict? Because it's easy to say between the two of us here, do this in conversation, but when people are out in the real world, you know, there's parties and different one-off events, and somebody might just have 100 grams of carbs one day and bump themselves out of ketosis. Would you say if that happens, that resets that 2 to 5 year time frame? Or is there a little bit of leeway there for people to have quote unquote off days?
So it's a really important question. From my experience, for people with severe mental illness, from my experience, in the first 6 months to 1 year, no cheat days are allowed. Period. End of story. Now, people will go ahead and cheat anyway, but they almost always suffer the consequences. Almost always, their symptoms come back with a vengeance. So that means their hallucinations and delusions were finally, once and for all, starting to get better. Maybe they got so much better that the person now thinks, I'm cured. I'm cured. I don't need this keto diet anymore. I don't need any of it. I'm cured. I'm going to eat whatever I want. They eat whatever they want. Within 24 hours, the hallucinations are tormenting them. They're louder than ever. They're like trying to drown them out. They're or they're suicidal or whatever. In those situations, first and foremost, I'm a psychiatrist and I make sure that the person is safe. And so we work on a safety plan and we do whatever we need to do to keep that person safe and keep everyone else safe. But I immediately get them back on a ketogenic diet. I might even encourage them to fast, do a water fast for 24 to 48 hours if they're open to that, because that is the fastest way to get back into a high level of ketosis. And I've been through that many times now with patients. And I want to just say that situation that I just described is the primary reason patients with severe mental illness can, in fact, do this diet and stick with it. One of the biggest criticisms of this diet from people is like, nobody can do a diet. Nobody can stick with it. I tried to lose 10 pounds and I couldn't stick with it. It was too hard. Well, yeah, it was too hard for you because you actually just losing 10 pounds is not that motivating and you don't really care that much about it. And you'd rather have your cake and you'd rather have your party with your friends. And so you can't stick with that diet. That normal person who's just trying to lose 10 pounds, yeah, I get it. It's really hard. For the patients that I'm working with, they are fighting for their lives. They're fighting for their sanity. When they break the diet and their hallucinations come back and torment them, 2 days later, they're saying to themselves, I'll never do that again. That party was awful. I'm not going to parties anymore. Or if I do go to parties, I'm just going to drink some like sparkling water. I'm going to drink sparkling water with a lime in it, and that's good for me. And I'll just eat my keto meal right before I go so that I'm not hungry while I'm there, and I'll be fine. But I'm never going to do that again because that was really awful. I almost ended up in the hospital or I almost ended up dead. And that is the reason why I can get patients with severe crippling mental illness to do this diet and stick with it. If they didn't have that negative consequence of breaking the diet, I wouldn't be able to get them to do the diet. Weight loss experts often can't get people to stick with the diet. Again, because the consequences of breaking it aren't that bad. Actually, they're rewarding. If anything, people feel better. Oh, it was such a fun party. I really enjoyed all that food and it was such a nice time. It's like, well, there goes your weight loss journey.
I hear what you're saying there with that piece of reinforcing this is working and adding that extra layer of motivation to stick to the diet from that point forward. But metabolically, having that bolus of glucose, does that reset the time frame? Do you feel like metabolically they need to go through 2 to 5 years again from that point? Or it's all part of that, 2 to 5 year period, even with the odd cheat day and that reinforcement?
No, if the cheat days are short-lived, 1 or 2 days, it by no means does that reset the clock. And the reason, again, so we know that with the epilepsy field, we know that with some other kind of areas. So the way that I think about it is that, again, I mean, we really don't know the precise mechanism of action of what is it doing and why 2 to 5 years? Why not 1 month? Why not 10 years? Why not a lifetime? Like what is happening magically during this 2 to 5 year period that is resetting the system and allowing people to then move on with their life and do whatever the diet they want and live happily ever after? We really don't know, but my strong speculation is it's this mitochondrial biogenesis and mitophagy and mitochondrial density, these issues. And that is just a slow process over time. And one cheat day doesn't like take your cell all the way back to complete utter mitochondrial dysfunction and dysregulation. It might take it back a little bit. It might stop the healing process for a few days. It might even take you a few steps back, but it doesn't reset the clock. Like you've done some of the repair. You've done some of the autophagy that needed to be done, but you haven't finished. You haven't really reset and reestablished a new normal for that cell yet. And that's what we're trying to do is we're not only trying to clean out all the waste, buff up the cell, but we're trying to establish a new normal for that cell, a new normal of resilience and function and regulation. And that process, I think I can say, based on the empirical evidence that we have with epilepsy for 100 years, that process appears to take 2 to 5 years for most people.
Okay, so for somebody that is going to go all in on the ketogenic diet, apply what we've been talking about today, the different levers, really give this a go. You quickly mentioned supplements. Any supplements you'd include along with all that to help facilitate these metabolic changes?
The two supplements that I most commonly recommend as augmentation with the ketogenic diet are magnesium and light salt. So a combination of sodium and potassium. So electrolytes can get depleted. A lot of people are deficient in magnesium anyway. So those are kind of standard pillars in my mind. Light salt, the combination of sodium and potassium has been found to reduce cardiovascular events in pretty good population studies, like in China, randomized controlled trials, I should say, in China. They've taken thousands of people. So I stand solidly behind those two recommendations. The other supplements that are plus or minus, depending on your lab values and other factors. So I don't universally recommend these to people. But the other ones that might get included are carnitine, creatine, and then there are lots of others. I mean, some people use CoQ10 or other CoQ supplements. Some people use different vitamins and anti-inflammatory agents and resveratrol. And I mean, there are all sorts of other things that are all related to everything we've talked about, metabolism and mitochondrial function. But I don't universally recommend those supplements. And the biggest takeaway I want to just say with supplements, because everybody hears a pill that you can take and then they don't want to do the other work and they just want to take the pill. Let me be clear. If you are not going to change your lifestyle and you think you're going to get away with only taking carnitine or creatine, good luck to you. I'm not wishing you poorly. If it works for you, great. What I can tell you is I don't think it's going to work, and don't be shocked when it doesn't work, because you're going to have to do the work. You're going to have to do the work to get it to work. And the work is changing diet and lifestyle and other things. And then the supplements can be added when needed, when you're doing the work and it's just not yielding the results that we should expect, or when you reach a plateau and something just it seems like you need a nudge to get to that next level. That's when some of these supplements, vitamins, can intermittently be good interventions.
How do you feel about urolithin A? There's a lot of talk in our world about that in general, and it directly relates to mitochondria. What do you think about it?
So urolithin A, it is a mitochondrial supplement that induces mitophagy and mitochondrial biogenesis. We have reasonably good data actually in elderly people that just taking urolithin A can increase muscle capacity. It can increase strength and muscle endurance. Just taking the supplement. Now, obviously, exercise is the better way to do it, but if you add some urolithin A with your exercise, you might get a little more bang for the buck. So I'm not opposed to urolithin A. Again, I'm often reluctant to talk too much about supplements because the takeaway for too many people is, oh, I'll go out and take that supplement and not do any of that other hard stuff. Or they hear that stuff and they're like, well, I'm on a healthy diet. Well, they're not on a healthy diet, but they tell themselves, I'm on a healthy diet. My diet is fine. I eat whole grain cereal every morning and I, with skim milk, and and I have my Nutri-Grain bars, which are ultra-processed foods that are loaded with sugars and other things. And they really do tragically think that they're eating a healthy diet because some dietitian told them that was a healthy diet, and it's not a healthy diet. So, and unfortunately, taking urolithin A probably won't do much for that. But yeah, as an augmentation strategy to promote mitochondrial health, especially if somebody just needs a little extra edge, yes, I am all for it. Do I think that urolithin A on its own will stop seizures? No. There's no reason for me to believe that urolithin A on its own will stop seizures, but a ketogenic diet will. Sometimes, at least. It doesn't for everyone, but a ketogenic diet can stop seizures. And that is really, really powerful and life-changing.
All right, Chris. Really good place to end it here. Really clear on that messaging at the end. These are adjuncts to supplements. We're going to link up your book, your YouTube channel, social media, website, everything in the show notes. Really enjoyed this. Thank you.
Thank you so much, Jesse.
Now that you're done, you're going to want to stick around here and catch this other incredible episode. You don't want to miss it. I'll see you over there.
If you've got PTSD, ADHD, OCD, eating disorders, early dementia, whatever the issue is, I will try to help you. My definition of a brain healthy diet is it has to nourish the brain, protect the brain, energize the brain. You can see dramatic